Hi, my name is Neha Monisha and this is my Physics 2212 Lab 4 on circuits. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, use different multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. We followed the instructions of the lab to obtain the following results in Part 1 and Part 2 to explore the voltage, current, and time dependency in an RC circuit. The results obtained in this experiment is the current through the circuit is 0.0208 amperes and the time constant is 7.46 seconds. The fundamentals used in this experiment is the node rule, which states current flowing in is equal to the current flowing out of the junction, and the loop rule, which is the sum of potential around closed loop is 0. We also use the Ohm's law, which states V is equals to IR. The assumptions of this experiment is that the resistance in the wires and ammeters are negligible. For this experiment, the system is the ammeter and voltmeter, and the surrounding is the circuit. For part 1, we set up the experiment in this manner with 2 batteries, 2 ammeters, and 2 resistors. The EMF of this experiment is 3 volts. The total resistance is 147 ohms. After we connect the circuit in this pattern, we can predict that the current in ammeter 1 and the current in ammeter 2 is equal, and it should be around 0.0204. From the lab experiment, we got 0.0208 ampere for I1 and I2. Reversing the connections in one of our ammeter will give us the negative value while the magnitude is same. When we convert one of the ammeters to voltmeter, the reading in the ammeter will be 0 since the circuit will be open. But the reading in the voltmeter will be 3 volts since we are calculating the total potential in the circuit, which is the EMF or 3 volt. Then we calculate the potential difference around the circuit by dividing the circuit up to these points as stated in the picture. We use the voltmeter to calculate the potential difference around the circuit, as we can see here. The current in the circuit here is 0.0204. The voltmeter does not change the ammeter reading because current does not flow through the voltmeter due to its high resistance, even though the circuit is being altered. The sum of potential difference across the circuit is 0, as we can see. This satisfies the loop rule, and the value of the current on the ammeter satisfies the node rule. Our experimental values also match the theoretical result as stated by the loop rule, which is 0. The approximate graph of the potential versus position is stated below, where it is a plateau when it is 0 volts, and it has a negative gradient when the voltage is negative and has a positive gradient when the voltage is positive. If the voltmeter is connected across the resistor with 10 ohms, the ammeter reading will show 0.02 ampere. If the voltmeter is replaced with an ammeter connected in parallel to the 100 ohms resistor, the current will increase from 0.02 ampere to 0.06 ampere since the current gets split due to the parallel connection. Using the Ohm's law, we'll calculate the resistance around the components as 43 ohms, 98 ohms. Resistance in the wire and the ammeter is 0 ohms. For the second part of this experiment, we are using an RC circuit to calculate the time constant. We are using an 8.3 ohm bulb, a 9 volt battery, and a 200 microfarad capacitor. When the battery is directly connected to the bulb starts to dim until it reaches 0 ampere. When the capacitor is directly connected to the bulb again starts to dim until it reaches 0 ampere. For the 8.3 ohm bulb, we can see that the charging time is 10 seconds and the discharging time is 15 seconds. When we take 2 of the same bulb, we can see that the charging time is 19 seconds while the discharging time is 28 seconds. After we linearize the data, we can get a slope of 0.134 for the graph. We know that the slope of the graph is the negative of the inverse of time constant, so using that information we can get the time constant as 7.46 seconds. The sources of error in this experiment could be the starting and stopping of the stopwatch, the estimated line of best fit, and the rounding of error in calculations. Now, what if we charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? If the resistor was removed, the ideal RC equation predicts that an instantaneous charge, because the time constant RC becomes zero, implying an infinite current. In reality, this cannot happen since every circuit has some resistance from the wire's battery, ammeter, and the capacitor's internal resistance. Using an ammeter in series, we can observe the current start high and exponentially decrease until the capacitor is nearly fully charged, about 5 time constants. The small resistance of the meter and components causes the charging to take infinite time, which explains why our measured value differs from the ideal prediction. Thank you.